There are many theories regarding the Big Bang and the birth of the universe, but recent observations from the James Webb Space Telescope have thrown these theories into question. I've used my understanding of math and physics along with AI-assisted analytics to create a hypothesis based on the new James Webb Space Telescope data, proposing that gravity may have played a much bigger role in the early Big Bang than we thought. These new findings could help us explore old questions about quantum gravity and resolve some of the problems surrounding dark matter, dark energy, inflation, and the creation of the cosmic web. So, what problems did the James Webb Space Telescope uncover about the origins of the universe? The James Webb Space Telescope found that massive galaxies and supermassive black holes existed far sooner after the Big Bang than current theories can account for. Astrophysicists had assumed the earliest large galaxies could only form after gas clouds became early stars, then slowly coalesced around gravitational centers to form early clusters and eventually evolved into larger galaxies. Many have also assumed that black holes started from the collapse of huge stars, called the small seed theory, then consumed galactic matter to become supermassive black holes. The recent observations by the James Webb Space Telescope indicate that both of these assumptions were wrong. To understand this, we need to look at the beginning of the Big Bang, starting when the universe was smaller than a single atom. This tiny space was a trillion times hotter than our Sun and contained everything that makes up the universe we observe today. In this proto-universe, the forces of gravity, the strong force that binds atomic structure, the weak force that drives atomic decay, and the electromagnetic force were all combined in a single unified state. As the proto-universe expanded and cooled, the force of gravity was the first to separate from the other unified forces. Everything else still existed as quantum waves of quark soup, and gravity was a pure quantum force, so exactly how it all behaved at this early state is still unclear, but the James Webb Space Telescope is providing new evidence from the earliest moments. After gravity, the strong force emerged to gather quarks into protons and neutrons, followed by the electroweak force, which then split into the separate weak and electromagnetic forces. Later, the proto-universe cooled enough for electrons to be trapped by atomic nuclei, forming the first hydrogen and helium atoms, then the Higgs field emerged. During this time, gravity must have done something unexpected based on the recent James Webb Space Telescope observations. This new data may help us understand questions we've been trying to answer about quantum gravity, dark matter, dark energy, and the cosmic web. This may be related to the role gravity and the other fundamental forces played as they first emerged from the unified state. We can actually see some of these early effects manifested in baryon acoustic oscillations, which left circular imprints in the early universe reflected in the cosmic microwave background. As the other forces emerged, eventually leading to atomic structure and mass, quantum gravity must have done something incredible to explain the James Webb Space Telescope data. It started collapsing the first matter in the universe to create hundreds of billions of primordial black holes. We've had the chicken and the egg backwards in several ways. These primordial black holes began producing vacuum energy as first postulated in Eraste Gleiner's 1966 paper on the energy-momentum tensor and vacuum-like states of matter. This vacuum, or zero-point energy, led to the rapid inflation of the universe. A recent theory describing this was presented in a 2023 paper by Duncan Farrar and Kevin Croker, titled Observational Evidence for Cosmological Coupling of Black Holes and Its Implications for an Astrophysical Source of Dark Energy. Most inflation theories suggest it was started by an unknown particle, but just as with dark matter and dark energy, this particle has never been detected. It's possible that as space-time expanded exponentially, these billions of primordial black holes became the seeds for the supermassive black holes that built all the galaxies in the observable universe. But how did this happen? Current theories suggest that the cosmic web was independently formed in some way to feed early galaxies with the dense gas required for star formation, but there is no evidence for this. If we assume that all supermassive black holes were formed while gravity still existed in a proto-quantum state, and that the emerging vacuum energy subsequently drove an exponential inflation of spacetime, spreading hundreds of billions of black holes from the size of a small point to the extent of the early universe, then some form of quantum entanglement may also have been involved in this process. I believe we can observe this gravitational entanglement as the cosmic web, which formed as the force lines of gravitational entanglement pulled in massive amounts of hydrogen and helium gas, making these lines of force visible. As clouds of hydrogen and helium were pulled in, they began to heat up and form stars which flowed toward the supermassive black holes to start forming all the galaxies at the same time across the entire universe. When we look back through time using the James Webb Space Telescope, we can see this galactic formation starting far earlier than we had assumed. Gravitational entanglement would also explain the anomalous galactic rotation curve currently attributed to dark matter. Normally, we would expect to see the stars at the edge of a galaxy move far slower than the ones near the center, but entanglement with these first black holes could make them rotate at almost the same speed. But what about dark energy? As matter is compressed to a singularity, some of it is producing energy according to Einstein's law of E equals mc squared. But this energy is not contained inside the black holes. It is spread across the universe as vacuum energy. This is driving inflation as theorized in the papers mentioned above and powering the vacuum fluctuations described in Heisenberg's uncertainty principle. As billions or possibly trillions of supermassive black holes continue to consume matter, the rate of inflation has increased, speeding the expansion of the universe. As universal expansion continues, inflation may slow again in an oscillation driven by the overall ratio between matter and energy across spacetime. Although this is simply a hypothesis based on the analysis of new data, I expect to see others draw these same conclusions and will be following up as more rigorous theoretical research emerges. Thank you for watching, and please like and subscribe to let me know that others are interested in this type of content.